So I have been, as you were kind enough to say in the introduction, working on a variety of things. But in the last 10 years, they've started to converge. And the theme they've started to converge around is the reality of time and the claim that fundamentally, and you'll see this emphasized over and over again from different points of view, time is fundamental. And by time, my co-authors and colleagues and I mean something close to what Henri Bergson meant. That is a real active time which is becoming and which creates, event by event, the history of the world. Here are some of the papers and some collaborators. We were just discussing Marina Cortez, who's a key collaborator in the construction of a type of theory called energetic causal sets, and we'll see their importance here. Recently, there are two, one is not listed here, very provocative, we hope, papers with Claudio Verde, and then you'll see there's more coming. Now, in fact, the way that we see it is there's a big research program based on the transformation of physics from the timeless or block universe point of view, which I think many of us originally shared as little baby children physicists before we grew up and began to think more seriously. And what I'm going to talk to you about today is sort of the core of the program. And the core of the program is closely related to fundamentals of quantum mechanics and pilot wave theory. But just, this is the last time I'll mention these subjects. The idea that not only is time the most fundamental thing, but laws are not fundamental, that laws change and evolve, goes back, of course, to Charles Peirce and other people. And there are important reasons why that is part of the program that I'm talking about. Although, unless there are questions, I won't get to talk about that. And similarly, the whole issue of whether fundamental physics is reversible or irreversible is core to the program. But then again, there's a number of developments which I won't get to talk about. Let's just mention them. This is a very important slide. This is the slide we shall go to when anybody asks for mathematical details, because I certainly don't have time to present them. That was supposed to be a joke. Okay, so I've been very happy to hear that philosophy is well respected in this community. So I indeed myself am very influenced by philosophers, and particularly by the notion of relationalism as it comes to us through Leibniz. So for me, the most important principles philosophically are Leibniz's general principles, say coordinated monadology, and the principle of sufficient reason, and especially I'll make very strong use of the principle of the identity of the indiscernible. And then just to show the power of the identity of the indiscernible, let's supposing, as we will in this talk, have an ontology of events. And events have causal pasts, which are a series of events that lead up to a present event, and causal futures. Now, supposing we have two events whose causal past are isomorphic. If we are determinists and believe that physics is deterministic, their causal futures must be isomorphic because their causal pasts are isomorphic. And if there's a deterministic law constructing the causal future as a function of the causal past, the causal futures must be the same. But Leibniz's principle of the identity indiscernible is exactly the opposite of that. It demands that the two causal futures be different if the two causal paths are the same. Otherwise, we have to identify the two events and we can't speak of two events. That's part of the power for us of starting with these principles of Leibniz. And when I need to, I'll hide behind them, as you'll see. Okay, now, there are many implications of these two principles. One of them is that there are no fundamental symmetries. And there are a lot of people, say in my generation or older, who are trained that the search for deeper knowledge or more unification in elementary particle physics is a search for larger symmetries. And this philosophy cautions us that, and actually it was Roger Penrose who first clued me in about this, that we should be looking for less and less symmetry as we go deeper and deeper in nature. And we'll see how this works out in the theory I'll be explaining to you. It's a theory of events where every event is unique in its properties, as the principles of identity and discernible calls us to do. So that's a very important difference that you'll see come out. Another one is that space and time are relational, but in different ways. For us, as we said, time will be fundamental, the most fundamental relation, and we'll think of time as a real, actual, active time, growing the universe. And space will be emergent. Space is somewhere way down in the list of things to care about. So we will be making very important use of a concept that is kind of stolen from Leibniz. We developed first with Julian Barber a long time ago. And that's the idea of the view of an event. An event is in some causal network. So when an event gives rise to future events and still future events, that imposes a causal ordering on the set of events. And we can therefore talk about the causal past of an event. And the information about an event's causal past, that it in some sense knows that you could measure at that event, we call the view of the rest of the universe of the event. So, and this is very important, that each event, as it participates in the laws to give rise to future events, has as its resource its past causal set. And each past causal set is in some sense the name of the event. Events don't have names like Lee or Jack or 37Q or whatever. Events, as a friendly relationalist, are determined by the view of the world that you have from that event, looking back into your past. So that's a very important concept, and we'll see that. Okay, well, we'll skip the one we just skipped. This is a little poem that I extracted from Leibniz, but given that I just lost a few minutes, let's just keep going. We can come back to that at the end. Okay, so in any fundamental theory, somebody should come back to us and say, okay, you claim you have a fundamental theory. What is fundamental in your theory? And what is emergent? What is constructed as emergent from the fundamental ingredients? So for our theory, what is fundamental, as I said, are events, the causal relations amongst those events, plus energy, plus momentum. There is no space, there's no space-time. There's a network of events and their causal relations, but we do impose that these events are endowed, and the causal relations from, say, event I to event J are endowed by energy, momentum, and perhaps other charges. And what indeed is an event? This is a rather recent thought that we developed with Cagliaverde. In the quantum theory, an event is first of all a process, something that happens in time, where some degree of freedom that is indefinite becomes definite. That is, we take the distinction between definiteness and indefiniteness of some observable that can be observed from an event as fundamental, and we'll see how we can organize everything around that notion of definite versus indefinite. So what is fundamental here? I'm just stating it again. Events, causal relations, energy, momentum. And emergent will be space-time, configuration, space, gauge fields, geometry, light cones, and quantum mechanics as well. And I'll be showing in outline how we derive quantum mechanics from these kinds of principles. And look at the bottom in particular, we have among our observables, in fact, or among our beables, energy and momentum. But we have no position, we have no embedding of events into space or in space-time. So we have no non-commutative algebra. We have no place for H bar to appear, and indeed H bar so far doesn't appear. Okay, so this framework, there are many different versions of it, And I'll show you one that's been published, the last few papers. It's called The Causal Theory of Views. And here are the basic ideas. And this slide repeats, but more precisely, we're out of the ingredients that I specified. That is, events, a network of events with causal relations, and paying particular attention to the views of events, which are the information about the causal past of an event that can be measured at that event. We want to do physics, we want to do dynamics. And there's no derivatives, there's no space, there's no differences, there's no distance between two particles. So how are we going to define the dynamics? And the only thing that we have available is the views of the events, which are the only beables. So we're going to construct a fundamental action principle only out of those, only out of the views of the events and differences between them. So there's a mathematical side. I told you I'm skipping the mathematical detail. Among the mathematical details that I'm skipping in the relativistic case, and this is in draft but not yet published, is how we think about the view of an event in a relativistic sense. And this connects to some mathematical technology which is being developed by other people recently, called the study of the celestial conformal field theory and things like that. But I won't be touching that in this talk. So here, this again is mostly repetition, but let me go to the top. How is dynamics defined? By what we're going to call a half path integral or a half integral, which is a sum over causal processes like a path integral. But we're integrating over energy and momentum, summing over the causal processes, but we're not integrating over position. So we call this a half integral, and I'll be giving you examples of it. And what replaces locality is difference in views. That is, rather than talk about the distance between you and me or the derivative of functions where I am, we're going to talk about the difference between your view of the past and my view of the past. And differences of those which are causally related are going to go into basically the kinetic energy. And what will go into the potential energy is what we call the variety of a set. The variety of a set is a measure of the distinctiveness of all the different views. That is, we sum up over all the pairs of views and put their distinction or their difference, which we have a numerical measure of. And that's in various guises going to appear as V, the variety. And just to tell you where we're going, that function on the original set of views when we construct the non-relativistic limit is going to become the Bohmian potential. So those of you who want to sort of guess how we get from here to there, that's the key result that makes this connected to quantum mechanics. Right. So again, we have an events ontology, events and their causal relations. And there's a big group of people working on that called causal set theory. Faye Dapper, Phil Sorkin, and others. And what we do is related to them, but we have more imposed structure because we impose energy and momentum living on the causal sets. That is, every event is endowed with some energy and momentum, and energy and momentum is conserved at each event and transferred to future events. And because of that, there is a conservation law at each event, and that will be important. And just to emphasize again, there's no space-time. There is geometry in this formulation, but the geometry is the geometry of momentum space. That is, in order to measure the differences in the distinction of views, we have to be able to put a metric on momentum space, or something like momentum space. Okay.